All right, friends and neighbors, welcome back to another networking video. Today we are covering chapter 21 of the CCNA certification course, Understanding OSPF Concepts. And hey, before we get started, if you're digging what we do here on the channel, consider giving a like and subscribe and visiting us again. With that being said, off to the OSPF concepts. So in this video, we'll take a quick look at the key topics we'll be covering. The exam section for this particular chapter is IP connectivity, but down in there, of course, we're really talking about what routers do. And so we're going to determine how routers make a forwarding decision. In this case, it's not default routes or static routes, but we have a routing protocol that we're about to deploy. So that means including things like administrative distance, routing protocol metrics, and then, of course, we're going to do OSPF v2. Now, the chapter talks about configuring and verifying the OSPF area. We're going to do a demo. We're actually going to build one, as always. We like a lot of demos. And we'll talk about what it means to be a neighbor, what it means to be a neighbor that's also adjacent, a little bit about point-to-point and broadcast connections or broadcast networks, and then the router ID. And we'll finish up with the do I, or do you know this already questions and the chapter 22 look ahead. So as you might imagine, the key topics have something to do with routing protocols. And so we'll be talking about what's the point of a routing protocol, right? What does it do? And then we'll talk just a little bit about interior and exterior gateway protocols, types of interior protocols and the metrics. And then we're going to go on down through, an OSPF build. So there's a lot to OSPF, right? How it gets started, how it works, things of that sort. So in addition to the demo, I'm also going to show you an actual packet capture, and we'll periodically look back at that sort of figure out where we are. So all of the things associated with getting an OSPF topology up and running is what we're going to talk about today. Now in our foundation topics, we're going to talk about how routers in general, and certainly OSPF specifically, decides to add a route. And what we're going to find out is that you don't just add a route because you're running a routing protocol. So a routing protocol is running, and there's an algorithm. There's a decision that has to be made as to whether or not something that you learn from your neighbors is going to be in your routing table and therefore becomes a routing table entry that you'll use to forward packets. So there are a couple of things that have to go on before that entry gets in there. Now, generally, there are three ways that we put or that routes end up in routing tables. And this doesn't really matter if it's Cisco or anybody else. And one of those is directly connected. So the minute you have an interface that's up, and it has an IP address, you get a routing table entry. And so that would be a directly connected route. And then if you go in there and manually do the IP route, destination network mask and then forwarding IP, that's a static route. And in that category is also the default route. So that's another way routes could get added. And then, of course, we have dynamic routes, which is what we're talking about right now. Now, the routing protocol has a couple of components as well. So we're going to see that routers exchange messages. Well, what's in the messages? It's information about things that they know or things that they want to tell you about. And so the parameters are going to be in those messages. And there are rules for when those messages go out, what the content is, and whether or not I agree to exchange information with you. And then there's an algorithm that gets run on the information that you just picked up from the network. So there's a couple of things that are part of a routing protocol. And at the end of the day, what we're after is a path selection, and what we want is the best path selection to all of the destination subnets. Wherever they are in our topology, we want to find all of those subnets and set up the best path to them. Now, the reason that we're talking about a routing protocol is that sometimes there are some terms that get conflated, right? Whether or not something can be routed or is routable, right, is different than a routing protocol. So examples of routing protocols are the routing information protocol, open shortest path first. So these are examples of routing protocols. things that can be routed is pretty much everything else that we put on the network. So anything that's got an IPv4 header in it or an IPv6 header in it, these things can be routed or forwarded by a router. So don't confuse those terms. All right, so what do we do with our routing protocol? Well, there's a couple of things that we want a routing protocol to be able to do. First up, you got to be able to communicate with your other neighbors. So there's networks that connect you to other routers. And so these might be your neighbors. And so if you are talking with a neighbor and you're both doing the same routing protocol, you're exchanging information about IP subnets that might be out there. So that's number one. The other thing that you want a router to be able to do is advertise information about subnets to neighboring routers. So we want to be able to collect stuff, and we also want to be able to send stuff out. Hey, by the way, I know about these things. I thought I'd share. Now, another thing that we want to do is, given information that we've received, what if we have more than one pathway to the destination? Now, we get in the habit of drawing these sort of flat or one-line sort of topologies, whether they're layer 3 or layer 2 topologies. But we have to remember that we could connect a bunch of routers in a loop, and therefore there would be more than one pathway to the destination. And so given that there's more than one pathway to the destination, we want to be able to pick the best one. Now, this chapter talks mostly about metric because we're comparing OSPF to OSPF. But what we have to realize is that sometimes we have the ability to compare OSPF to other types of networks or other types of methods that we've learned a route to a network. So for example, if I learn something via RIP version 2 or EIGRP and OSPF, I have to have a way to compare them. And the way that we do that is with admin distance. And then if everything else is the same, right, is there something else that we could use? Well, it turns out that the big dog, the thing that's over everything else, is the prefix length, meaning that we want to be able to have a mask that gets us closest to the destination. Now, technically, that's not part of this chapter. That's just a little foreshadowing. Now, the last thing that we want our routing protocol to be able to do is if there's a network topology change, we want to be able to react to that. So if a router dies, or if we lose a connection, or if we add something, right, we want to be able to update everybody as to what happened. And so the routing protocols have a lot of stuff built into them to respond to changes in the network. So a couple of keywords and tricky phrases. Neighbor is somebody that's connected to your same link or network. So if I can run a line between two routers, or if they connect to the same switch and the same VLAN, they're neighbors. Now we often talk about convergence, right? The topology is finally converged. Well, that just means that they've gone through the process of determining the best routes to all the destinations. So interior and exterior gateway protocols. These are the two general categories. It turns out that most of the routing protocols that we talk about are interior, meaning that they're designed for use in a single autonomous system. Now, if you run an organization and you control all the routers and you're running a routing protocol, you could say that you have an autonomous system, that you are in charge of all of that. And then at some point on the edge of your network, you have a router that connects to the ISP. All right, but your organization is your autonomous system. Now, your autonomous system might be given an AS number by IANA. It's not always the case. Autonomous system numbers are used by things like the Border Gateway Protocol, which is an exterior routing protocol. So it's not always necessary that we have an autonomous system number, but the fact that you're running your own set of networks and your own routing protocol means that you sort of have this autonomous system. All right. Now, an exterior gateway protocol is used between autonomous systems. The only exterior gateway protocol that we have is the Border Gateway Protocol, or BGP4. It's the one that runs on the internet. It's also been tasked to run in data centers where there are lots and lots and lots of networks. So we don't normally run border gateway protocol on our autonomous system networks. So you would run OSPF or EIGRP instead. Now, the reason that we're talking about interior and exterior gateway protocols is because routers used to be called gateways. In fact, we still use the term default gateway to mean a router. But really, we're talking about routing protocols that run inside an autonomous system or in between autonomous systems. Now, let's say you're setting up your autonomous system. You got a bunch of networks that you're connecting together. You don't need an ASN. You just want to hook up a bunch of routers together and run a routing protocol. The advantage of running a routing protocol is that it automatically responds to changes, and it's a lot harder to make mistakes than if you were going to run around to 100 routers and try to do all the static routes, right? That's a lot of work. So that's probably the big reason why we turn on routing protocols. But now you go, okay, cool, which one should I use? Well, there's a couple of basic ways that we compare them. We could say, well, what kind of routing protocol is it in terms of the algorithm? And there are generally two sides to this coin. There's distance vector, right? Magnitude and direction. The network that you're trying to get to is 10 hops away and it's that away. Then there are things like link state that give you a little bit more information. In addition to understanding maybe how far something is away, you understand the cost associated with using that path to get to that destination subnet. And then there's things that are in the middle, advanced distance vector or hybrid. So examples of distance vector protocols, the famous one is RIP, the Routing Information Protocol. RIP version 1 and RIP version 2, really all that they care about is how many routers did you go to get to that destination. Link state is what OSPF is. The other way to think about these things is who invented them or who are they associated with. So distance vector protocols are often called Bellman-Ford, and link state protocols are often called Dijkstra, or they say, well, that's using the Dijkstra algorithm, which is the shortest path first. The other way to compare them is what is the metric? Well, RIP, as I said, uses hop count, which is sort of a simplistic measurement, right? It's just this many routers away. But there's no information in there about the links over which they pass, the cost, the throughput capacity. Nothing in there is provided. Now, OSPF uses cost, which is a sum of the bandwidth of the outgoing interfaces. So now all of a sudden you go, oh, this number that I have is based in part on the speed of these links or the capacity of these links. So automatically you get more information about them. So that's another way to compare routing protocols. And we often want to use things like link state protocols today. So OSPF is probably the most popular routing protocol out there. There aren't very many folks that use RIP anymore. Now there are other ways to compare routing protocols, right? We already talked about interior versus exterior, but whether or not they use or can use variable length subnet masks, whether or not they summarize routes, right? Whether they will glue routes together if it's to a larger address space. What is the update address that they use? Will they have to talk to each router individually, or can we use a broadcast or multicast address to tell everybody what's going on? And then, how long does it take to converge to a stable topology? So RIP is kind of slow, as an example. OSPF is faster than RIP because OSPF has a whole bunch of mechanisms that are not present in RIP to speed up convergence. So let's get into some OSPF specifics. Now, as we said, the name of the game is to find out how to get to all the different subnets or networks out there. And so to do this, we need to know the topology. So link state routers or OSPF routers communicate everything with each other. You'll see when we take a look at packets here in a second, they blast everything out. So they've got multicast addressing that they use to get to everybody very quickly. But they can also talk directly to a neighbor router and exchange information that way. Now the blasting everything out, we call that flooding. which is a way or a mechanism to let everybody know what's happening very quickly. And then periodically, every 30 minutes or so, routers will reflood, right? Just in case something changed that was missed. Now, all of this information is exchanged via something called a link state advertisement. Now, link state advertisements are in a message called a link state update. There are lots of different kinds of link state advertisements that we can put inside a link state update. And in fact, you can do multiple LSAs inside an update. Now, what a router does is it collects all of these link state advertisements and puts them in its link state database. And the goal is for all the routers in the topology, all the routers in the same area, to have the same link state database. So what we want to make sure of is that everybody knows how to get to all the subnets. And we do that by exchanging all of this information. OSPF has sort of this three-step process that it goes through to get to this point. The first one is that we got to become a neighbor. So a router will come up and say, hey, I want to talk OSPF. And then a router that's on the same network will say, hey, you want to talk OSPF? I want to talk OSPF. Let's talk OSPF. And so they do that. They're neighbors. And then they say, well, wait a minute. Are we going to talk the same OSPF? Same parameters, same configuration? Are we set up the same way? And so they exchange databases as well. So we have these database description messages. We'll see those here in a second. And then we say, well, what do you know about the topology? And if one of them knows more than the other one, or they know different things, then they will exchange LSAs to make sure that they eventually wind up at the same link state database. And then, once we have the link state database, now we're going to process the information in the database and discover the best possible routes to the destinations. And those are the things that get added to the routing table. Now, the idea of OSPF neighbors is one of the important parts of the chapter. So just because two routers are connected to the same network or the same link does not necessarily mean that they will become neighbors. Neighbors is sort of the first step, right? It's introductory. So the two routers that want to become neighbors have to be compatible. They have to be in the same network or VLAN. They have to both be running OSPF and the same version of OSPF, and then similar OSPF parameters or configuration. If they've gotten to that point, now they're willing to swap information. Now, how do you know if all of that is set up correctly? Well, routers introduce themselves to potential neighbors via the hello message. So the hello message has your configuration items in it and some details about you. And so a potential neighbor will see that, compare what it knows, and then it'll send out a hello message as well. Now, the hello messages are sent to a special multicast address, 224.0.0.5, and you can take a look at all of this information with a show IP OSPF neighbor command in your router. Now, through this process, routers also learn each other's router ID. So there's a couple of things that happen. You realize that you're communicating with a particular IP address, but that IP address might not be the router's ID. So OSPF adopts usually one of the IP addresses of the router. Remember that the router can have more than one IP address. So the router adopts one of those IP addresses as its ID. It's automatic. Then that is used in the messaging. Now, this is a configurable parameter. You can tell a router what its router ID is. Now, here's the funky thing about OSPF. It doesn't use TCP or UDP. So it is encapsulated right inside an IP packet and has an IP header protocol ID of 89. Now, I think at this point it's a good idea to take a look at some packets. All right, so here is a capture that I've done between OSPF routers, and I've filtered on OSPF, so that's all we're going to look at. And you can see that these two routers are 192.168.3.253 and 3.254. So imagine that you got two routers, they're just connected to each other on the same link or the same VLAN. So whoever's first comes up, right? It's the first router that's been configured and sends out an OSPF hello packet. So let's take a quick look at this and we can see the encapsulation here. It is just IPv4 and then right to OSPF. And in the IP header, scroll down a little bit here, we can see that we have the protocol ID of 89. We can also see that this is going to the multicast address of 224.0.0.5. Well, what is in a hello packet? There's a couple of details here. We have priority, we have some timers, and then we have the neighboring addresses, right? So this was a neighbor on its other side. We also have things like the source, the area here. I used area 51, haha. So there's some details about how this router is configured and where it is in the network. There we go. So we have some details about the router. And then here are some options that this router is willing to support. Its neighbor, its potential neighbor, sees this and sends out the same information. Well, at some point they decide that they're going to give the thumbs up to being neighbors. And so now they're going to swap the database description messages. Now these messages are trying to describe further details about the OSPF configuration, but of course, they're also trying to figure out what is in or what should be in the link state database. And what we see after that is some link state requests. And what they're doing is they're saying, all right, I see that when you were describing yourself to me, that you had stuff in your link state database that I didn't have. So they send out a link state request, and then they get an update back. And this goes back and forth until finally they both have the same link state database. And then they drop right back into hellos again because things have converged. They've figured out that they're compatible neighbors, but that they have the same link state database, which is one step beyond being a neighbor. That is what we call establishing an adjacency. We'll talk more about that in a bit. Now, the chapter spends some time on the two-way state. So a router receives a hello from a neighbor with that router ID listed as being seen by the neighbor. And a potential neighbor has passed all the checks and the settings in the hello, meaning that we look at the items that are in the hello. I see that you want to do OSPF the way that I do, and I'm going to send you a hello message. And once they've done that, they've reached what we call the two-way state. Now they'll exchange link state databases. In other words, they're saying, all right, there's a link state database that is the final version for our area. Let's make sure that we both have that link state database. So that's accomplished via the database description messages and then the link state updates that provide all the link state advertisements for all of the things that we ought to know or things that ought to be in the link state database. Now, once everything is updated, then we're going to drop back into those hellos as we saw. But we're not done, right? The hello messages are a check. They're sort of a heartbeat, right? I'm still here. Oh, my neighbor is still here. I'm still here. My neighbor is still here. So we have two sets of timers now that we're paying attention to. The hello timer is how often I send out hellos. But the dead interval or the dead timer is how long I'm willing to wait before I believe that something happened to my neighbor. Something has occurred. And that is usually 4 times the hello timer. So if I don't hear from you for a little while, I'm going to assume something happened, and then I'm going to reconverge my topology. As always, we're going to watch for changes, updates, right? New routers, bad routers, links that go down, things of that sort. And even if everything is fine, we're going to occasionally reflood. Now, one other detail, and I realize that we're getting a little bit long on details here, but we're going to try to remember to do all of these in the demo, is this idea of designated routers. Now, OSPF has 2 general types of network. We have a broadcast network, and then we have a point-to-point network. Broadcast networks, we really don't know who else might be out there. It could be just one other router, it could be no routers, it could be a whole bunch of routers. So the default is to be a broadcast network. So in a broadcast network, OSPF routers elect a designated router from all of the OSPF routers that are out there and a backup designated router. And this election occurs based on the priority setting and the router ID. Now, what's the point of a designated router? Well, if you had a whole bunch of routers, let's say we have 10 routers, and they're all connected to the same set of networks. Well, it gets a little tedious if everybody is advertising everything. So the designated router is elected to be the source of all routing information. And the backup designated router is there in case something happens to the designated router. So other routers are not sourcing, they're not sourcing all of the routing information for the area. Any router that's not a designated router is called a DR other or a druther. Now, the ability to use the multicast address to flood everything to everybody and the designated router to be the one that makes the exchange of Link State databases makes OSPF more efficient in getting the information to everybody. We can also use the only designated router's address of 224.0.0.6. Now, we talked about the two-way connection. If the routers have exchanged the databases, they've now reached what's called the full state, and this is one of the questions for the chapter, and they've established an adjacency. They're not just neighbors, they're adjacent. So one thing to remember is that not all neighbors are adjacent, but all adjacencies are neighbors. So calculating the best routes with the shortest path first algorithm. So you can think of the Link State advertisements, the ones that come across in the Link State updates, as part of a puzzle. They're only part of the picture. What the router does is gathers all of those in, and once we believe that we have a complete Link State database, we're going to run the shortest path first algorithm against all of that information. Now, you don't have to do the math. You don't have to run Dijkstra's algorithm. But this is the famous problem that comes up when we talk about this is the traveling salesman problem. What would be the best way to get to all of the cities on your route to be the most efficient? And that's sort of the basis for the Dijkstra algorithm or the base problem. So you would consider what is not only the best path, but the least cost path to get to all those cities. Even though you don't have to do the math for it, you should be able to look at a topology and, given the link speeds, the capacity of each link, you should be able to take a look at them and go, oh, what's the cost to each destination from a particular router or from a particular perspective? That's what the router is going to do. Now, importantly, the cost is based on the outgoing interfaces. There are some default costs that are helpful to us. On 100 megabits and 1 gigabit Ethernet connections, the outgoing cost is just 1. For 10 megabits, the cost is 10. And from this, you might suspect that the lower the speed, the greater the cost, and that will be accurate. If you're just on an Ethernet topology, you can sort of expect that all of your costs would be multiples of these numbers. Now, as I said, if you are running a bunch of networks and you're in control of it, you have an autonomous system. An OSPF autonomous system is made up of areas, but it's very, very common, especially for small to medium size, not overly complicated autonomous systems, to just run one area. It converges quicker, but it's very sort of straightforward to deal with. So how do you figure out what your area is going to be? Well, as long as we follow a couple rules, we're in good shape. Anytime two routers are connected together and they share the same link, the same subnet, they're going to be in the same area with each other. Areas should be contiguous. They should not be broken up, right? We don't have, area 1 separated by area 0 and then area 1 again. That's not how it works. Now, area routers can be inside the area, right? Deep inside the area and connected to a whole bunch of networks that are inside the area. Or they can connect to another area as well. That would make them an area border router. There is a special area out there called the backbone area. It's always area 0 or 0.0.0.0 because a lot of times we use an IP-based sort of schema. They're not IP addresses, they're area IDs, but we use that schema, so you'll see it both ways. Now, the benefit of using areas is that the calculation of a topology in an area is a little simpler than trying to just add a whole bunch of networks to the area, no matter how big or how complex it is. So once you get to a certain level of complexity, when you start breaking things up, the calculation in the Link State database for a particular area is easier. But when you do that, you still have to receive information about the networks that are in other areas. All right, the Link State Advertisements. We've mentioned these a couple of times. There are a couple of base types in RFC 2328. That's the OSPF v2. But we're only going to talk about 3 of them today. For the most part, an area is made up of routers and the networks to which those routers are connected. So the 2 very, very important Link State advertisements that we have are the router LSA, which tells us about a router and all of its connections. And then there's LSA type 2, or the network LSA, which describes a network that has a designated router and a backup designated router. These LSAs are created by the designated router. Now, if you have multiple areas, then you'll also have a type 3 LSA called a summary LSA. So when it comes down to it, if you have one area, router LSAs are going to be there, network LSAs are going to be there, and they'll define the intra-area topology, or the intra-area topology. If you have a single area topology, you will not see summary LSAs. All right. Now it says demo time here. Let me take a quick review of those packets and then we'll do the demo. So here's our packets again, right? We started off with hellos and then we said, well, now that we're going to be neighbors, maybe, let's exchange our databases. And then we see this link state request. Now the link state update comes along and says, here is what I know. Now we can see a couple things here. One is, here's the number of LSAs. And a link state update can carry more than one LSA, but this one happens to be a router LSA. And this is information about this particular router, and then connections for this particular router. And here is another link state update that has a single LSA in it. This one happens to be a network LSA. So this is information about a particular network. So who are my attached routers to this? Who did this come from? What is the mask associated with this network? So there we have it. So there's our 2 basic types of LSA. All right, let's take a look at that demo. Now, as we go through this demo, I'll try to remember to do all of the things, all of the topics that we had there. But essentially what we've got here is a topology with 1, 2, 3, 4 networks out there. And I have 3 routers connected to this multi-layer switch inside here. Now I haven't done any OSPF configuration. And if I take a look at my routing table, I can see that I have 2 directly connected networks. So what I'm going to do is start configuring my routers and we'll watch what happens in the simulation. Now in an OSPF configuration, the first thing we have to do is say, well, I'm going to do a router OSPF process. I'm going to give it a process ID. So we'll give it process ID number 1. And we've got a bunch of options that we are going to work with here. The default is going to be OSPF version 2. I'm not going to worry too much about that. I'm also not going to set the router ID for this demo. That'll be next chapter. But what I am going to do is say my network is going to be the networks that I want to advertise. Now, from the perspective of router 0, the thing that I absolutely don't know about is the 11 net over here. So I absolutely want to advertise that one so that my neighbor can learn it. Now OSPF uses a strange mask. We'll spend more time on that next time. It's part of the look ahead. Now once we get the network and the mask in there, I will show you the question mark, right? It wants to know what area we're going to use here. Now, when you're using a single area, what you're going to do is configure it as area 0. And I can either put in area 0 like that or 0.0.0.0. There we go. Now take a look what happened here. The minute I did that, it wants to generate an OSPF message. Well, what is the OSPF message? And we'll remind ourselves about a couple things, right? This is going out to a multicast address. The protocol ID is going to be specific to OSPF. Remember that's hexadecimal that we're looking at there. And we can see right over here it says that this is an OSPF hello message. Now right now this router is wondering if there's anybody else out there that also wants to do OSPF. Now while I'm here, I'm also going to advertise the 12net. And that's because I don't know who else might be connected here. So we're going to advertise both of these. Now if we watch for a second, right, these messages go out in opposite directions because we want to tell the 11net about the 12net and we want to tell the 12net about the 11net, but we're not there yet. We're just trying to find other OSPF routers. And we will do this periodically, right, based on our hello timer. And we can see here that I've got a hello interval specified, and I don't yet have a backup of designated routers because I'm not talking to anybody else yet. All right, let's go back to real time and we'll set up our other router. Now if we take a look at the routing table of router 0, you're probably curious, oh, did it learn about the 11net? And the answer is no, because even though there's an OSPF router in the topology, we have not yet configured router 0 to be an OSPF router. So they're not exchanging any information yet. So let's teach this router a little bit about OSPF, and I'll give it a process number. Now the process numbers can be the same, but it doesn't really matter. Now I'm going to do my simulation here again so that we can see what happens the minute I do OSPF on this router. So we're going to say network. Now this router will advertise the 12net also on area 0. And we can see that right away we got an OSPF message out there. But we also want to advertise the 13net into the OSPF topology. So we're going to do that one as well. Okay. So now if we watch what's happening, router 0 sends out OSPF hellos. Router 1 sends out OSPF hellos. And they've now discovered each other. Now if we take a look at what's going on now, they're beginning to realize that there might be another router out there. Now, all of a sudden, because they're wanting to talk to each other, we've picked up a designated and a backup designated router. These two routers happen to be on the same network. They're the only two candidates out there for a designated router and a backup designated router. So if we go a little farther, oh look, we've got a change in color here. Well, what kind of messages are these? So what we've done is we just got past the two-way phase, or the two-way connection. And now we've got OSPF DDs out here, database description messages. So now we're starting to understand a little bit about each other's link state database. So if we just let this go back and forth a little bit, we would eventually see that the two routers would say, well, what's in your link state database? What's in mine? And we're looking for the change in message. It's a little hard to see. There's the link state advertisement right there. So this is an LSA type 1. Remember that the two that we will be looking for if we were going to filter through all of these would be the LSI type 1 and the LSA type 2, the router and network LSAs. And everybody's in the same area, so we would not have the summary LSA. So this goes back and forth for a little while longer as they get their databases updated and everybody knows what's going on. And then eventually we would drop back to the OSPF hellos. And we can see here it's an OSPF hello, but if we take a look inside the packet. Now, one other thing that I sort of missed, should point out to you, is that a lot of these messages are going to the multicast address, but if we look earlier on, when the two neighbors were establishing their adjacency, they were communicating directly with each other. Right? So this was unicast messaging between the two. Well, let's take a look at the routing tables. Now, I suppose it's worth noting here, loading to full. That means that they've established their adjacency and they've completed the exchange of the Link State database. So we went from hello, is anybody out there, to the two-way status to now full. So now I can do a show IP OSPF neighbor, and I can see that I've got a neighbor ID here, and the IP address that I use to get to that neighbor is 12.254. And what that indicates is that this is the router ID, but I'm communicating with this interface on the router. So it's not always perfectly clear which interface is going to be the router ID. This is also why we sometimes configure the router ID. We specify it. Let's also take a look at the routing table. And now we have an O here. We have the OSPF route, and right there is the metric. The metric is 2. So what router 1 is realizing is that it can get to the 10.1.13 network, and the cost to that network is 2. Well, what is that really talking about? Remember that it's the sum of the outgoing interfaces. So from the perspective of router 1, how do I get to the 13 net way over here? Well, I go out this interface. This happens to be a gigabit Ethernet interface. So the cost of this interface is 1. The cost of this outgoing interface is 1. 1 plus 1 gives me 2. Now, the last thing that I'll point out here is what happens when we bring up another router. So I'm going to configure this router quickly. We're going to say router OSPF 4. We'll say network, and we're adding the 14 net. So we'll say 10.1.14.0. And also in area 0. And we'll do the same thing. We'll add it to the 12 net as well. That's the other interface there. Well, we're running real time right now. And we see that this is now full. It's loaded to full, right? And so this router, which was late to the party, now knows about everybody. And the other routers should also know about the 14 net. But if we take a look at the capture, we can see that our designated router here is 10.1.11.254, which is the font of all of the information. Now they're figuring out who maybe the backup designated router might be. But here we have 3 routers, and only one of them is going to be in charge of all of the Link State database information. And so when routers are communicating and getting updates and trying to understand what the Link State database proper should be, it's only going to be one router. And if something happens to that one, the backup designated router will fill in. So I guess the last thing I'll note here is that this entire topology, right, is kind of small, just 4 networks, but it represents an autonomous system. It is a single area autonomous system, but there you have it. All right, did you know this already? Questions. Which of the following routing protocols uses link state logic? Well, by now we know that that was OSPF, and that was D. Which of the following routing protocols use a metric that is, by default, at least partially affected by link bandwidth? And that is both the hybrid or advanced distance vector and OSPF, so C and D. Which of the following interior routing protocols support variable length subnet mask? Well, that was everybody except RIP version 1. RIP version 1 was what we call class full, so everybody else now does variable length subnet masks. Question number 4. Two routers using OSPF v2 have become neighbors and have exchanged all LSAs. As a result, router 1 now lists some of its OSPF learned routes in its routing table. Which of the following best describes how router 1 uses those recently learned LSAs to choose which IP routes to add to its routing table? Remember that at this point, we have an updated link state database. And so now what we have to do is run the shortest path algorithm against the LSAs. Which of the following OSPF neighbor states is expected when the exchange of the topology information is complete between two OSPF neighbors? Okay, when they first figure out that they can be neighbors, that is the two-way thing. Once they do that, we saw in the routers that they've exchanged link state database, we're now full. And our last question for this chapter, a company has a small, medium-sized network with 15 routers and 40 subnets and uses OSPF v2. Which of the following is considered an advantage of using a single area design as opposed to a multi-area design? It's just simpler planning, makes life much easier. Now, from a performance perspective, right, the multiple areas might be able to calculate their link state databases quickly or more efficiently. They would still need those summary LSAs, but a single area autonomous system in this case just makes life much simpler. Okay, the chapter 22 look ahead. So now that we've got our arms wrapped around the single area OSPF and we've seen the messages and we sort of know what to expect, we're now going to implement some features of OSPF. We're going to talk a little bit more about that wildcard matching, verifying operation, and then we'll look at multi-area and we'll configure some of those router IDs so that we know which one is going to be used. All right, this has been pretty cool. We've been building to this for a long time. We got static routes under our belts, and now we got our first OSPF topology. Now, I've done a number of OSPF things on the channel, and I'll link a bunch of those in with the show notes. But this time through, we did our OSPF basics, right? Areas, autonomous systems, messaging, the link state database, link state advertisements inside a link state update, and then how an OSPF area is put together. And then, of course, we did our demo. Like and subscribe if you're ready to go with some more OSPF and you want to support the channel. I'd appreciate it. May those packets always reach their destination, no matter how many areas you have to go through or how many link state advertisements you need to get. And remember, even though this is OSPF, it might be new to you. You can do this.